Hello, and welcome to Lesson 10 of this Introduction to Linear Algebra with Wolfram U. The topic of this lesson is the inverse of a matrix. So let's begin with a brief overview of the lesson. So in the previous lesson, we have talked about matrix multiplication. And in this lesson, we'll talk about the inverse for matrix multiplication. So just like you have the inverse of a number or a reciprocal, we also have the notion of an inverse for matrix multiplication. So here's an example that illustrates the idea. So let's say you have a 2 by 2 matrix over here, A, with first row 3, 5, and second row 4, 7. Then what you can do is to compute the inverse of the matrix using the inverse function in the Wolfram language, and you get back another 2 by 2 matrix. Now, the point is that when I say that that's an inverse, what I mean is that if you do a dot product of the matrix A with its inverse, then you get back not the number 1, but something that looks like the number 1, but is really the identity matrix, in this case of order 2, with 2 rows and 2 columns, and ones along the diagonal. So that's the idea of the inverse, and the inverse of a matrix will be used in this lesson to solve matrix equations. Okay, so let's begin with a formal definition of the inverse. So let's say you have an n by n matrix, a square matrix. Then this matrix is said to be invertible if there is another matrix B such that A times B and B times A both give you the identity. So I over here refers to the identity matrix of order n with diagonal entries equal to 1 and all other entries equal to 0. And this matrix B over here is called the inverse of A, and it's got a notation which suggests that it actually is the inverse. It's written as A to the power negative 1. Okay, so as an example of an invertible matrix, so you've got a matrix A over here, and I set up the matrix B in this manner over here, and now I check that if I do A dot B, or if I do B dot A, then in both cases I get back the identity matrix. So the relation for the definition is satisfied, and so certainly you have the inverse in this case. But let's confirm the result with inverse, and you do get back just the same answer. Okay, so now if you have a matrix which is not invertible, then it is said to be singular. So singular matrix is a matrix which is not invertible, and that can happen in two ways. The first way it can happen is that you actually have a matrix which is not square. So here is the matrix A, and that is not a square matrix. In fact, it has 2 rows and 3 columns. And if you try to find the inverse, then the inverse function complains that this is not a square matrix. So there's no answer given in this case. Now, another way you can have a singular matrix is if the so-called determinant of the matrix is 0. So here you have a 3 by 3 matrix. It's certainly square, but if you try to find the inverse, you get a complaint saying that this is singular, and that's because the determinant, which is det over here, is 0. Now what that means will become clear later on, but the main point is that the determinant is a number that determines whether the matrix has an inverse or not. So we'll talk about these determinants in more detail in a later lesson. But for now, let's talk about some simple cases where you can actually do it, and that's the situation where you have a 2 by 2 matrix. So if you have a 2 by 2 matrix, that over here, A, B, C, D, then its inverse has got a very nice, simple, closed form. So basically what you do is you kind of flip the diagonal elements. You have DA over here where you had AD over there, and you change the sign of each of these elements over here, and you divide by AD minus BC. And of course, if you're dividing by 0, then you have a non-invertible situation. So this number over here is called the determinant of A. Okay, so for example, you have a matrix over here, 1, 2, 3, 4. So let's compute the determinant. And then you follow the rule over here. So you do 1 over determinant. Then you flip the diagonal elements and you change the sign of the remaining 2, and you get back the inverse. Let's check with the inverse function, and you do get back just the same result. So 2 by 2 matrices are rather simple to invert. You can use this formula over here. You simply flip the diagonal elements, change those two signs, and divide by the determinant. Okay, another class of simple matrices are the so-called elementary matrices. So those are matrices which are obtained by doing a single elementary row operation on the identity matrix. So for example, here is a matrix, and it's almost like the identity except you've got a 5 over here. So basically it's done by doing the operation R3 goes to R3 plus 5 R2 on the 3 by 3 identity matrix. Okay, now such a matrix is always invertible. So basically what you do is you try and transform it back to the identity matrix, and that's very simple. What you do over here is you simply replace the 5 with a -5. And let's check that you actually have an inverse. And of course, that seems to be true over here. But in general, what you need to do is to apply the idea of row reduction to get the inverse. So if you're given a matrix A, just any matrix at all, then what you do is you form the augmented matrix by putting the identity matrix over here, and then you try and do row operations. And if you're successful, then you get back the A inverse right over there. That's a very nice, neat procedure. Now, if that fails, then the inverse does not exist. So for example, here's a matrix A, which is 3 by 3. And what you do is you simply place the matrix over here on the left, put the identity matrix on the right, like I said over here. So you have the augmented matrix, A and I, and you do a row reduction. And you see over here that on the left-hand side, you now have the identity matrix, and what you have on the right-hand side is just the inverse. Let's check that, and you do get back just the same answer with inverse. So given an arbitrary matrix, you can use row reduce to find its inverse. Okay, so now some properties of inverse. So if you take a matrix and you invert it and you invert it back, assuming that works, then you get back the original matrix. Now if you have two matrices A and B, you might think that A times B inverse is A inverse into B inverse, but in fact it's the reversed order over here. That's because those two operations kind of need to be computed carefully, and you have just the reverse direction over here. So if you do A B inverse, that's B inverse times A inverse. And you can either do a transpose first and then inverse, or vice versa. That doesn't matter. Okay, so as an example for those properties, you have two matrices A and B over here. Let's check that if you do the inverse of A, you do get back the matrix A, which is correct over here. Then if you do inverse of A dot B, that's inverse B dot inverse A. So notice I have got the reversed order over here. You have B and then A. And finally, if you do the transpose followed by inverse, or inverse followed by transpose, you get back just the same result. Okay, now the whole point over here is that you want to solve linear systems with the inverse. So let's say you have an invertible matrix A, and you want to solve the system AX equal to B. Then this system has the inverse, A inverse times B over here, and then you have that as a solution for the whole system. Okay, so that's a little bit like what you do in algebra. You simply divide by A, and that's done by A inverse over here. So let's say you have the system over here, and what you do is you form the matrix A for the coefficients, so 8, 9, 5, 7, like the coefficients over here, and the matrix B, which is the right-hand side, and then you do inverse of A dot B, you get back the answer, 1, 2, and you can check the answer with linear solve, and you get back just the same result. Now, that's a really neat procedure, and in fact, it works for matrices of any order. So let's say I take a random 6 by 6 matrix. I take a random right-hand side. I solve the equation with the formula, and I check the answer with linear solve, and you do get back the same result in this case as well. So the inverse actually gives us a wonderfully clean way of solving linear systems or matrix equations. Okay, so that's the end of this lesson, and the main point is that a square matrix may have an inverse under the operation of matrix multiplication, and whether that exists or not depends upon the determinant for the matrix. Now, you can find the inverse quite easily in special cases, but in general you require to use row reduction. And of course, there are several useful properties that relate the inverse to multiplication and transposition, which we saw in an example early on. So that's the end of this lesson, and in the next lesson we'll talk about LU factorization, a very important operation. But before doing that, do revise inverses. They are critical for linear algebra, and knowing them well will really help you. So I'll stop over here. Thank you very much.